Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Shahid Latif, Associate Professor at Department of Computer Science, Sarhad University, Peshawar. Today we will start lecture number 4 of Electronics 1 course. The course code for Electronics 1 is ELC216. This course is offered for second semester of various programs including BS Computer Science, BS Software Engineering, BS Telecommunication and BS Electronics. Electronics 1 is 2-1 credit hour course, means that we have to cover 2 hour theory while 1 credit hour or 3 contact hour of lab work per week. Course details are such that today we will learn the lecture number 4 of week number 2. The topic we will cover in this lecture is conduction in semiconductor materials, or we can say that current flow in semiconductor materials. Before starting our new lecture, let's have a look on the previous lectures, lecture 1, 2 and 3. As you know that in lecture number 1 we discuss the prerequisite courses required for this course or for Electronics 1. These prerequisite courses include AC circuit analysis and DC circuit analysis. We discuss some important topics from AC and DC circuit analysis courses. Then in lecture number 2 we start our course from the course book or textbook of electronic devices. We start chapter number 1 of our course entitled as Semiconductor Basics. In lecture number 2 we discuss the atom and the structure of an atom. We also explain the Bohr model of an atom, similarly the atomic number of any atom, the electrons and shell in atomic structure. Similarly, we also discuss the valence shell and its valence electrons, and finally we discuss the ionization process. In lecture number 3 we discuss or we learn the classification of matter based on their conductivity. We classify the matter in 3 distinct groups, that is insulator, which cannot conduct electric current, the conductors which can maximally conduct the electronic current, and semiconductors which sits in between the insulators and the conductors in terms of their conductivity. Or we can say that semiconductors are those material which have some properties of insulators while some properties of conductors. Or we can say that semiconductor material is neither a good conductor nor a good insulator. Then we discuss the energy bands, specifically the valence band and the conduction band. We also discuss the gap which is known as an energy gap or band gap between valence band and the conduction band. And finally in lecture number 3 we discuss the covalent bond, which is used in the crystalline structure of silicon or other semiconductor material. Today we will start our lecture by discussing the conduction in semiconductor materials. We will also discuss what is electron and hole. What does it mean by electron-hole pair? And how electron and hole recombines, means the recombination process of electron and hole. In this lecture, we will also discuss two types of current. Current due to electrons, which is known as an electron current or simply electronic current, and current due to the holes, which is known as a hole current. Recommended books for this course includes Electronic Devices, authored by Thomas L. Floyd. We are using 9th edition of this book. If you have any latest edition, it is also acceptable. Remember that Electronic Devices, authored by Thomas L. Floyd, has two versions. One is known as a conventional current version, while the other one is known as an electron flow version. Remember that most of the contents of this lecture are taken from the conventional current version of Electronic Devices book. Starting with current in semiconductors. As we know that electrons of an atom can exist only within prescribed energy bands, means that electrons of an atom exist in various energy bands which are already prescribed, like in first shell or first energy band, in second shell or second energy band, in third shell or third energy band, and so on. Each shell is separated from adjacent shells by some sort of band gaps. Remember that there is no electron in these band gaps, means that electrons cannot exist in these band gaps. Figure 1.12 shows the energy band diagram for an unexcited atom. Unexcited atom is that one which has no external energy, such as a heat energy or a light energy or any sort of external energy. So the figure 1.12 shows the energy band diagram for such unexcited atom in a pure silicon crystal. Remember that this condition, where the energy bands of an unexcited atom are shown, occurs only at absolute temperature of 0 Kelvin. Here you can see that in this figure an energy band diagram is shown for an unexcited atom in a pure silicon crystal. Remember that there are no electrons in the conduction band. Here in this diagram we can see that the lower part of this diagram is representing the nucleus. The first band or the first shell has 2 electrons, because we know that atomic number of silicon is 14. So in first band or in first shell there will be 2 electrons. In second shell of silicon atom there will be 8 electrons, while in third shell or in third band, which is also termed as a valence band, there are 4 electrons. At absolute temperature there will be no electron inside the conduction band. If we increase the temperature from the absolute temperature, then we may find some of the electrons inside the conduction band. The conduction electrons and holes. We will learn that what are the conduction electrons and holes. An intrinsic or pure silicon crystal at room temperature has sufficient heat or thermal energy for some valence electron to jump the band gap from valence band into the conduction band and become free electron. These free electrons are also called the conduction electron. As we discussed in previous slide, that at absolute temperature the conduction band is empty, but at room temperature, where we have some sort of heat energy, there must be some valence electron, and they will gain the heat energy, and they will jump from valence band to the conduction band, and they will become free electrons. Then these electrons will be known as the conduction electrons. This concept is illustrated in energy diagram presented in figure 1.13a and in bonding diagram presented in figure 1.13b. Here, when an electron jumps to conduction band, a vacancy is left in the valence band within the crystal, and this vacancy is called a hole. Thus, for every electron raised to the conduction band from valence band by means of some external energy, there is one hole left in the valence band, and that electron and its vacancy, which is termed as a hole, create an electron-hole pair. To understand this, let's have a look on the figure 1.13a and b. Figure number 1.13a is representing energy diagram. Here you can see that in valence band there are several electrons. By gaining the heat energy from our environment, some of the valence electron jumps into the conduction band and they become free electrons. These free electrons leaves a hole or a vacancy in valence band. This free electron and its vacancy, which is termed as a hole, is known as the electron-hole pair. Similarly, you can see that in bonding diagram, an electron leaves the crystalline structure and become free electron by gaining heat energy from the environment. Again, this free electron and its vacancy, which is termed as a hole, is termed as an electron-hole pair. Recombination is the process of recombining things. In terms of atoms, we can say that a recombination occurs when a conduction band or free electron loses its energy, which is gained from the external resources, and that free electron falls back into a hole in valence band. So this process is known as a recombination process. As illustrated in figure 1.14 of our textbook, here a piece of intrinsic silicon at room temperature is considered. This piece of intrinsic silicon has a number of free electrons. These free electrons are not attached to any atom, and these free electrons are essentially drifting randomly throughout the material. Also, an equal number of holes in valence band are created when electrons jumps into conduction band. We have already learned previously that when an electron of valence band become a free electron, so it will leave a hole behind. So the number of electrons in conduction band and the number of holes in valence band must be equal. Here in figure number 1.14 we can see that an electron-hole pair in a crystalline structure of silicon. The free electrons are being generated continuously while some recombine with the holes. Here you can see that in the right upper portion we can say that generation of an electron-hole pair occurs, means that an electron from the crystal leaves its valence band and become free electron, and it leaves a hole behind. So an electron-hole pair has been generated. Similarly, there are several free electrons which are drifting randomly throughout the crystal. Again, here you can see that the recombination of an electron with a hole occurs. When the free electron loses its energy, it falls back into valence band and recombine with the holes. Electron and hole current. First we will learn the electronic current, or simply the electron current. When a voltage is applied across a piece of intrinsic silicon as shown in figure 1.15 on next slide, means that we are applying some external voltage to a piece of intrinsic silicon. We know that in that piece of intrinsic silicon there are thermally generated free electrons in their conduction band, and these free electrons are free to move randomly in the crystal structure. These electrons are now easily attracted toward the positive end of the power supply. This movement of free electron is one type of current in a semiconductor material, and that movement of electron or current is called electron current. In this figure you can see that we have several free electrons which were initially moving or drifting randomly throughout the crystal. When we apply some external voltage sources, these free electrons are now directed towards the positive end of the power supply. So the current or the electronic current produced by the movement of these thermally generated free electrons is known as electron current. The hole current. The other type of current is hole current. This type of current occurs in valence band. Here holes are created by freeing the valence electron. We have already discussed in previous slide that when valence electrons moves to the conduction band and become free electrons, they leaves hole behind. So here are holes which are created by free electrons. Electrons in valence band are attached to their atoms, means that they are not free to move in crystalline structure. As we know that some of the electrons which were attached to their atoms in valence band, these electrons can move into nearby holes if they have a little change in their energy levels. Thus, when these valence band electrons leaves their original position and move into a nearby hole, so they leave another hole behind where these electrons came from. Effectively, it seems that the hole has moved from one place to another in the crystal structure, as shown in figure 1.16. Remember that the current in the valence band is produced by valence electrons. Still, it is called hole current. A reason behind that is to distinguish the electron current and the hole current, or simply to distinguish the hole current from the electron current. Thus, conduction in semiconductor is considered to be either the movement of free electron in the conduction band, which is termed as a electron current, or the movement of holes in the valence band, which is termed as a hole current. The hole current is actually the movement of valence electrons to nearby atoms, creating hole current in the opposite direction. And this can be understood using the diagram on the next slide. But before going to the diagram, remember that there is only one type of current in conductors: the movement of free electrons, because there are no holes in the metallic crystal structure. In lecture number 1, we discussed that most of the conductors are metals. So in metals, there are free electrons available even at room temperature. So the movement of free electron is the movement of free electron, and the current due to these free electron is the only current in conductors. There is no possibility of hole current in conductors. This diagram shows the hole current in intrinsic silicon. If you can see that mark 1 is representing a free electron which leaves a hole in valence shell or valence band of its atom. So this free electrons is now in conduction band, while the hole which it leaves is located in valence band. To fill this hole, a nearby atom marked as a 2 moves into this first hole and leaves a second hole behind. Now a hole is at position number 3. At mark 3 we have a hole, and to cover or fill this hole, a valence electron moves into that second hole and leaves a third hole behind, which is marked as a 4. Now again a valence electron moves into that third hole and leaves a fourth hole behind. Similarly, you can see that at mark 5 a valence electron moves into the fourth hole and it will leave a fifth hole behind. At mark 6 a valence electron will move into fifth hole and it will leave a sixth hole behind. So you can see that there are two types of flows. The one flow is shown in a pink color, which is representing the movement of valence electron to its nearby holes. We can say that when a valence electron moves left to right to fill a hole while leaving another hole behind. So that movement seems like the hole has effectively moved from right to left. In this figure, the gray arrows indicate effective movement of a hole. As we discussed that there are two types of movement. One is the movement of valence electron from left to right, while one is the movement of holes from right to left. Actually, the valence band electrons moves from one to another place, but effectively it seems that a hole is also moving from right to left as shown by the gray arrows. This effective movement of hole is known as hole current. Thank you very much. That is all for today. If you have any query or any question, you can ask me through shahid.csit@sood.edu.pk. Once again, thank you very much.